Hi all, this is a video for arithmetic logic circuit design. Okay, so ALU circuit is very important because it's a basic block for the processor. And it is basically a combinational circuit. In other words, ALU does not contain flip-flops because flip-flops is only for the sequential circuit. Okay, so this is the general symbol we use to represent an arithmetic logic unit. A and B are the inputs of the data that we want to process, and mode is the input that control the functions of the ALU. For instance, there is an addition mode, subtraction mode, and so on. For outputs, the main output is the result, which is the data, type of data that represent the result of the computation done by the ALU. Beside the result as the output, we also may have a single bit output like 0, overflow, carry out that represent the status of the result. So modes of the ALU may include addition, subtraction, and bitwise logical operation. So normally we combine arithmetic and logic operations in a unit of ALU because they share many logics. So these are the steps that you can consider when you want to design an ALU. So first, we need to be clear what functions we want to include in the ALU. We can list the function in the form of table, like for example, we want to design an ALU that consists of A and B, the AND operation, OR operation, and the addition. We can list them in a table. Then we can set the mode value for each function. Okay, so we list down the function here and set the mode value we want to design for each mode of or each function of the ALU. Then we determine the logics needed. For example, in this case we need an AND gate connecting A and B for the AND operation. We need an OR gate for the second mode, and we need an adder for the third mode, which is the A plus B. And then we determine the size of the multiplexer. So basically we'll see how many functions in the table, then we will guide us on the size of the multiplexer. In this case, we need 3:1 multiplexer. But in some of the cases when you have sharing logic, the multiplexer size could be reduced for the optimization purpose. Then the next step will be to connect the components to the multiplexer, and if you need to add the additional selection logic, then you have to do that as the last step. Okay, so make sure you label all the signals of the input outputs. Okay, now let's look. Then if we have a ALU, the ALU we have can only process a single bit. Okay, like this one, we have only one bit A, one bit B that produce one bit result. So if we put mode equal to 0, then the mode of AND gate will be selected, and it will do the AND operation. So 0 AND with 1, the result will be just 1 bit 0. So this is not very practical, as normally we will duplicate the slice ALU. This is what we call slice ALU because it processes only 1 bit. So we normally will duplicate the slice ALU to N duplicates or N copies so that it can function as the N bit ALU. So if we have the them connecting with where the carry out of the ALU connect to the carry in of the next ALU slice, then we can make the ALU to process multiple bits. For example, if we put mode equal to 1, which is the OR operation, then it will take all the A0, A1 until A31 to be OR in a bitwise operation with the bit 0, bit 1 until bit B31, and the result will be OR 1 because 0, 0, 0 OR with 1, 1, 1, we get 1, 1, 1. Okay, now let's look at another example of the ALU slice where it contains 4 modes or 4 functions, which are AND operation, OR operation, addition, and subtraction. So for the when we refer to the number of functions, there are 4. So the direct implementation seems to just using the 4:1 multiplexer. Okay, so AND will do the first mode, the first function, and OR will do the mode, the second function, addition or adder for the addition, and subtractor for the subtraction. However, this is not an optimized solution, as we have learned that adder also can do the subtraction function, and at one time we don't need all the units here to work. Okay, we don't need all the 4 units here to work. together. At one time, we just need one of them to work. So why we need so many units? So because at one time we only need one unit. So if we can share those units, then we better share them for the optimization purpose. AND gate cannot be shared with the OR gate because they are totally different gates. But we know that adder can do the subtraction function. So this to get a more optimized solution, we can use only one adder, and with the additional little gates that control when the adder should do the addition, when the adder should do the subtraction. Okay, so we have now more optimized ALU solution with just one unit of adder instead of one adder plus one subtractor. Okay. And we control it using mode 0, okay, because we see here mode 0, when mode 0 equal to 0, it functions as adder. When mode 0 equal to 1, it functions as subtractor. So we can utilize mode 0 together with XOR gate to control when the B should go to the adder, or when B bar should go to the adder. So if we have mode 0 equal to 0, then B will go to the adder to perform the A plus B. When mode 0 equal to 1, then B bar will go to the adder to perform A plus B bar, which we need in the two's complement process. So let's look at how to use this slice ALU to build the n-bit ALU. Okay, so previously we add the XOR logic here so that we can control when to pass the original B to the adder and when to invert the B. Okay. So this is because this process is part of the two's complement process. When we want to perform A minus B, we using the adder. So actually we are performing A plus inverted B and plus 1 at the ALU least significant slice. Note that the plus 1 only happen at the one of the slices of the ALU, not all the slices. The slices is the slice of the ALU that need the plus 1 is the least significant slice. And in the XOR gate we mentioned in the previous slide is the XOR gate to invert each bit of B to B bar. And we haven't done any plus 1 on the ALU slice. This is because we cannot put the plus 1 in the carry in of the ALU slice. If we do so, we will, and then we duplicate this ALU for say 4 copies to perform the 4-bit subtraction, then we are getting into trouble because we have fixed 1 at the ALU slice, and this 1 will add 1 for each slice of the ALU, which is slice 0, slice 1, slice 2, and slice 3. This is not what we want for two's complement process, as mentioned, because two's complement process just need a plus 1 at the least significant ALU slice. So we cannot put the plus 1 at the ALU slice. We will only implement the plus 1 after we duplicate the ALU to the multiple bits. In the example at the right hand side, say for example we duplicate 32 times for the 32-bit ALU. So the plus 1 need only to be implemented on the least significant ALU as highlighted here, not the second least but least significant ALU, which is only on this ALU that process the least significant bits of the data. Okay, so the plus 1 here need to be only implemented on the carry in of the least significant ALU. Okay, so now how to implement the add 1, the plus 1 here? We cannot just put 1 here as the constant 1 will fix the 1 for all the modes of the ALU, no matter is A plus B or A minus B. This is not what we want, so we need to control when we want the plus 1 through the mode signal. So if you can see here, the mode signals that differentiate between A plus B and A minus B is the mode 0, bit mode 0. Okay, so we can utilize the mode 0 bit put in the carry in here, so that when mode 0 equal to 1, okay, then it will do the A minus 1 function. Then mode 0 equal to 0, it will do A plus 1. So don't worry that the mode 0 equal to 1 will affect the OR operation because the mux multiplexer will not choose the result from the adder if the ALU is in the OR operation. Okay, so when mode equal to 0, 1, which is during the OR operation, the carry in which is also 1 at that time, will not affect the result of the ALU because the ALU that time will only performing OR bitwise operation, and the mux will only take the result from the OR gate. So the carry in 1 here won't affect the final result of the ALU. Okay, as mentioned earlier, so the output of the ALU does not consist of the result only, but it also consists of some single bit flags such as 0 flag, overflow flag, and so on, and also the carry out. Okay, let's look at one more example of the ALU. So this is another example of ALU where it consists of 3 arithmetic functions: a plus b, a minus b, and a plus 1, and 1 logical function which is NOR bitwise operation. So to design, first we need to list down the functions clearly that we want to include in the design. Secondly, we need to make sure the mode values are clear, not just use the symbol, but we list down 0, 0 represent the mode signal for a plus b, 0, 1 for a minus b, and so on. Next, we determine the arithmetic components and the logical components required in this design. So in this case, from here we see that we can in the most optimized solution we can just have one adder. Okay, of course in the straightforward solution you want to put 3 adders, but if the solution normally need to be optimized, then we just need to use one adder because as mentioned so previously, you don't need to normally ALU don't perform all the 3 arithmetic function at one time, so you can share just 1 unit of adder and 1 NOR gate. Okay, so next we determine the size of the multiplexer. So normally you look at how many functions or 4 functions, then you determine 4 to 1 max. No, it is not necessary. It's not always correct, because in this case, if you have determined 2 units of components only, then you just need 2 to 1 max. Okay, and 2 to 1 max because the first input handle the arithmetic result and the second input will pass over the NOR result. Okay, so if you look at the NOR operation, the mode is m equal to 1, 1. So we can control the select signal by using the AND gate, because when m equal to 1, 1, then it will select the NOR result, and otherwise it will just select the arithmetic result. Okay, then we connect the components that we have decided to the multiplexers, and next we need to add the other logic that will help us to do the selection. So in this case, you will see here the adder that have x and y as the input. Not especially, the input y does not connect directly from B. This is because the y does not necessarily receive B as the input. It depends on the modes of the adders. Okay. So over here, you need to compute or derive the additional logic that will help you to decide what is the value of y. Okay, so you can put the additional column here, put y, and then put what should be the value for y of the adder for each mode. So when a plus b, of course, y will get b, right? Y will get b, so that a plus b can be performed. And when a minus b, y will get b bar. Sorry, there's a bar on top here, not clear, b bar. Okay, and when a plus 1, y will get 0, y. Okay, let's look at here. When a plus 1, the plus 1 happen only at the least significant slice. So we shouldn't fix the 1 at the ALU slice. Otherwise, it will create a plus 1, 1, 1, 1 instead of plus 1. So when it is in the a plus 1 mode, then the y should receive 0. We will only fix this 1 when we use the ALU slice for the n-bit ALU implementation. So based on the table of considering the mode signal as the input and the y column as the output, we can derive a logic for y in terms of the mode signal and b. Okay, so this table is small, just follows. Then you can use the SOP method: m1 bar, m0 bar, b M1 bar, M0 bar, B, or with the second row, M1 bar, M0 and B bar, okay, and to compute the logic for Y. Okay, this don't care, you can consider 0. So 0, 0, you don't need to consider in building the SOP. Okay, so here you will at the end simplify the equation, you get M1 bar in the end with the XOR of M0 and B, okay, as illustrated here. Okay, with so, and don't forget the labeling, like here, don't forget label A and B, don't forget label carry in, carry out, and result. And with this, then you complete the design of the ALU slice. Okay, now let's say you want to expand the ALU slice to the n-bit ALU. Okay, then remember after you build the n-bit ALU, you need to solve is there any additional logic you need to put here to generate the carry in for the least significant slice of the ALU. So if you look at the function table, you need the +1 at the least significant slice when the mode is 0, 1 and 1, 0. Okay, so you can use the OR gate, okay, connecting with the mode signal, so that when it is 0, 1 or 1, 0, the carry in here will be 1 to execute the +1 at the least significant slice. Okay, now next, let's move to the extended topic on ALU. So sometimes in the real application, there are some logic that control what modes of the ALU we need. It could be the instructions that control whether the ALU should be in the addition mode, subtraction, and so on. It could be some components like comparator and so on. So let's look at the first case where we use a comparator to control what modes we want for the ALU. Okay, now let's consider that this is another ALU, not the same as any previous examples of this previous slides. Let's say this ALU has 3 functions only, which is A minus 1, B when 0, 0, A plus 1 when 0, 1, A plus B when 1, 0. Okay? And then let's say in this application, we use comparator to decide what modes the ALU should be. So we want the comparator to decide the ALU mode based on the comparison result. Okay, let's say if A less than B, we want the ALU to do the addition. A greater than B, we want the ALU to do the subtraction, and otherwise do the A plus 1. Okay, so we have this table and we have the ALU mode table, a function table. So to derive the logic that produce the correct mode signal based on the comparison result. So you need to derive the truth table that has the result of the comparison as the input, okay, and the signal M1 and M0 as the output. Okay, so comparator output EQ and GR will fit as the input to this logic we want to design, and the output of the logic will be based on the desired mode that we want to produce, or we want to control at the ALU. Okay, so when comparator result is A less than B, the comparator output will be equality equal to 0, greater equal to 0. So this 0, 0 means comparator result is A less than B. So at that time, we want to produce mode signal 1, 0. Why? Because mode signal 1, 0 means addition will happen, okay, which is as the same as the specification table here. Okay, when A greater than B, we want the subtraction to happen. So when A greater than B, the comparator output will be EQ equal to 0, GR equal to 1, greater. Okay, then we want to produce mode signal 0, 0 so that edit subtraction can perform. Then lastly, when it is equal, where EQ equal to 1, we want the A plus 1 to happen. So this logic block will produce M1 equal to 0, M0 equal to 1. Okay, with this truth table, which you derive based on the specification table here, will lead you to the solution that consists of this NOR gate and a wire. Okay, because at this truth table, to produce M1, okay, we look at M1 column. Okay, to produce M1 equal to 1, then we need the EQ equal to 0, GR equal to 0. So this truth table here can be realized using just NOR gate. Okay, this NOR gate will solve M1, and for M0, if we look at the column of output M0, 001, the same as equality 001, then the solution is just a wire connecting the equality to the M0. Okay, so with this additional lock, then we can control how we can control the ALU modes based on the result of the comparator. Another case is, let's say the ALU mode is controlled based on the instruction. So normally in such application, you will be given the instruction code. Say for example, 00 represent add instruction, 01 represents sub, 10 represent increment, 11 represent NOR. So you're given the instruction code in this system, and then normally you also be given the information of the mode signals for each function of the ALU. 000 ALU will perform addition and so on. Then to connect the instruction to the ALU, in other words, to allow the instruction to control the mode of the ALU, then you need to design an instruction decoder. Okay? Instruction decoder. The instruction decoder will read in the instruction code and produce the right mode signals to put the ALU in the correct mode. Okay, so you can take out this column put here as the input of the truth table of the decoder you want to design. You take out this mode column put here as the output column of the truth table. So this truth table represents the instruction decoder you want to design. So when 00 happen at the instruction code, you want the instruction decoder to produce 000 because 00 correspond to the instruction add, and you want the ALU to be in the addition mode when instruction add happen. When instruction sub happen, you want the ALU to perform subtraction. When instruction code is increment, you want the ALU to perform A+1. And when the instruction code is 11, you want the ALU to perform NOR operation. Okay, so you have this truth table that represent the instruction decoder, and if you are asked to design until the end using Verilog, then you can use the case statement to code the truth table into Verilog. So the last example will be the example that control the mode of the ALU through the simple keypad. It has the plus button, minus button, and up button. Up button represents the increment. And in such case, when you want to link the button to the mode signal of the ALU, then you need to design an encoder that encode the signal of the button being pressed to generate a code that will correspond to the mode of the ALU. So just need to build a truth table where the input represent the signal coming from each of the buttons. So we have 3 buttons here, so we have three inputs here. I2 represent the signal from plus button, I1 from minus button, and I0 from up button. And the output of the truth table is the mode signals and the corresponding mode signals related to the button being pressed. So when the button I2 or button plus is pressed, then we want the mode of 10, because the mode of 10 is addition mode for the ALU. And when the second button, the minus button, is pressed, then we want the mode subtraction, which is 00 in the design of this ALU. And lastly, if we press up button, we want the increment or A+1 to be performed, which is 01 as specified by the ALU function table. So if you are asked to complete the design of the encoder in Verilog, then you can just use the case statement or the if-else statement to code the truth table in Verilog. Okay, that's all for the video on ALU. Thank you.